In this lecture, we discuss a technique for creating filters called the windowing technique. A window function is any function that is used to truncate a signal to n samples. Up to this point, every time you've used just n samples of a signal, you have truncated the signal with what is called a rectangular window. I'll show the advantages of other types of windows for the creation of filters. I'll discuss windowing techniques for creating filters while using a low-pass filter as my primary example. However, this method can be used to create any type of filter. We have previously shown that if we want to create an ideal low-pass filter, the filter coefficients will be a non-causal, infinitely long sinc function. However, since we often do not want to implement such a system, we must choose to make the system causal by shifting the sinc function and then truncating the sinc function to n samples to minimize computation time. If we truncate the filter coefficients to n samples with a rectangular window, then the frequency response of the filter will develop a set of ripples. These ripples lower the resolution of the system, so we want to reduce the height and width of these ripples as much as possible. If we take a closer look at the system, we see that the width of the main lobe is 2 pi over capital N, and that the height of the first side lobe is 13 decibels smaller than the main lobe. Since these ripples are created by truncation, it is tempting to believe that we could reduce the height of these ripples by increasing the length of N. Unfortunately, increasing the length of N reduces only the width of the ripples. The way to reduce the height of the ripples is to use a function whose truncation of the signal is less abrupt. The first option for decreasing the height of the side lobes is to window the function with a triangle. We choose the triangular window because it decreases slowly to 0, unlike the rectangular window. For the sake of comparison, let's remember that the main lobe and side lobes of the rectangular window looked like this. Now, the main lobe and side lobe of the triangular window would look like this. As you can see, the height of the side lobes shrunk considerably, but the width of the main lobe widened. Unfortunately, no matter what window we use, we will always have to choose the side lobes and increasing the width of the main lobe. A window function that finds a near ideal compromise between these two trade-offs is the Hamming window. The Hamming window is essentially a cosine function that is raised by a DC offset. Since the Hamming window is a smooth function at all points, it further reduces the height of the side lobes while very slightly increasing the width of the main lobe compared to the triangular window. Let's examine the frequency of the low-pass filters windowed by different functions. If we have the low-pass filter G sub D, then the truncated filter would have the following form. There would be ripples in the passband and stopband. These transitions from the passband to the stopband would also not be abrupt. Truncating the filter would create what we call a transition band. If we used the Hamming window instead, the ripples would be reduced in the passband and the stopband. However, the transition band would be widened by a factor of 2. To recap, when we used the windowing method for creating filters, we essentially used a shifted windowed sinc function as the basis of our filter. Then, our choice of windowing function forced us to choose between decreasing the ripples in the stop and pass bands and having a wider transition band.